Okay, I can see people are still joining, but I think it's time to start. So welcome to SAZERAC, the last day of the 2021 edition. We're at session 5A today. We're going to be hearing about escape fractions, ionizing photon productions, and also 21 centimeter observations. And so just a reminder to everyone, we'll have 10-minute talks, and then you can ask questions on Slack. So go on the Slack SAZERAC 2 5A channel, and then you can see the different threads where you can post your question for each of the individual talks. And with this, without further ado, I would like to introduce Rohan Naidu, who is he's a PhD student at Harvard, and he's going to be talking about double bubble Lyman trouble. Go ahead, Rohan.
Good morning, good afternoon, good evening, everyone. My name is Rohan Naidu. I'm a final year PhD student at Harvard. Most of the work I'm going to present today is in close collaboration with Yorit Mate. And I have the immense privilege of being supervised and advised in all my endeavors by Charlie Conroy and Pascal Louis. So this talk is going to be a talk about escape fractions. Escape fractions are our single greatest hurdle to progress when it comes to understanding cosmic reionization. By escape fractions, I mean the fraction of ionizing photons that are produced in these early star-forming galaxies that then make it out of their ISM to reionize the IgM. And you can see you have very radically different reionization histories that are possible depending on what the escape fraction properties of galaxies look like. So if bright galaxies are efficient reionizers, you end up with reionization by the oligarchs. Versus if it's faint galaxies that are the most prolific producers and also escapers of ionizing photons, then you end up with something like a more democratic, smooth reionization. And progress on escape fractions has been so difficult because direct observations are impossible at higher redshifts. And even at slightly lower redshifts, things are really complicated because of the stochastic nature of the IgM. So you only have lower limits to individual sources. So what we often do is we look for indirect estimators of Lyman continuum escape. And the highest fidelity indirect tracer in recent years that has emerged is the Lyman-alpha line profile. In particular, a very tight peak separation in the Lyman-alpha profile seems to be a very efficient predictor of escape fractions. Another related feature in Lyman-alpha profiles that you see in some of these most prolific leakers is a central component in the Lyman-alpha profile. So to capture this, we introduce a new metric called the central Lyman-alpha fraction, which picks up all these very extreme sources as having very high central Lyman-alpha fractions. The idea is that this is basically tracing ionized channels through which the Lyman-alpha can just directly escape. So putting these two indicators together, the Lyman-alpha peak separation and the Lyman-alpha central fraction, we are able to very efficiently pick out high escape galaxies versus low escape galaxies. And this is really powerful, right? Because Lyman-alpha is very easy to measure compared to Lyman continuum. And it completely circumvents this whole IgM stochasticity problem that really hampers these high redshift studies. But what you need to access these Lyman-alpha profiles is high resolution. So you need spectra that are R greater than 4,000. And you need systemic redshifts, so you know whether your central Lyman-alpha is indeed central Lyman-alpha. And this is precisely the data set that the X-Shooter Lyman-alpha survey at Redshift 2, PI'd by Yorit, has put together. So this is really gorgeous data. I'm showing you the Lyman-alpha profiles here of the entire sample. The resolution is high enough, the systemic redshifts are precise enough that you can do this business of using Lyman-alpha profiles to infer things about escape fractions. I want to highlight that the sample is very well defined. It's flux limited. And because this is the gorgeous X-Shooter instrument, you get coverage all the way from Lyman-alpha to H-alpha. So you can do things like measure Balmer decrements and measure Lyman-alpha escape fractions. So we apply these metrics to the XLS sample, and we pick out the high escape sources and the low escape sources. So about 35% of our sample has profiles like these, which don't have any flux at all at the line center, very wide peak separations, likely very low Lyman continuum escape. And about 50% of our sample has these really interesting profiles where you have a lot of Lyman alpha escaping right at the line center, very narrow peaks, so very likely to have high escape fractions. And so now what we want to do is we want to set up this very controlled kind of A/B test where we have all these low escape sources and these high escape sources. We want to stack them and study the spectral features that emerge in the median stacks. This is what the stack looks like for Lyman alpha. So of course, by design, the profile is concentrated around line center in the high escape sources. In the low escape sources, it's a much more broader profile. The peak separation is very high. I also want to emphasize that both these stacks have comparable stellar mass, comparable MUV, comparable beta, comparable gas phase metallicity. So the differences between them can't be attributed to these properties, at least within the dynamic range that we explored. As two sanity checks that what we are doing is really working, the stacks differ in their dust content greatly. Remember, we picked these stacks based purely on their Lyman alpha profiles. No other selections were made, and we see that they differ greatly in dust content. So this is a good sanity check that what we're doing is really working. Another really stringent sanity check comes from the Lyman alpha escape. So the Lyman alpha escape acts as an effective upper bound on what your Lyman continuum escape can be, at least near the Lyman edge. And we see that the upper bound to Lyman continuum escape in the stack is basically 10-ish%, versus here, it's more like 45%. So now we move on to other spectral features and see what the differences between these stacks are. So MgII has attracted a lot of attention lately because it might be a very sensitive indicator of escape fractions, and it'll be accessible with JWST at very high redshifts. And indeed, we validate the immense promise of MgII. In our high escape stack, we see the MgII is basically emitted at no velocity offset, and the doublet ratio is very consistent with a low column density. Versus in the low escape stack, we see the MgII is really redshifted by about 130 kilometers, and the doublet ratio is consistent with having basically a high column density. Another really striking difference between both the stacks is in their O3-2 ratio. So the literature around O3-2 has been a bit muddled, right? There's been like promise, and then there's been pessimism. But what we find is a very, very clear difference between these stacks in terms of their O3-2. In the high escape stack, you have a factor of 3 greater O3-2 compared to the low escape stack. The log U, which is the ionization parameter implied by this very high O3-2, is comparable only with the superstar clusters as a population, as per Lisa Cooley's amazing review. The feature I'm the most excited about, though, is the extraordinary stellar hardness that we see in the high escape stack. So we see nebular carbon-4 and nebular helium-2 in the median stack. So I want to really emphasize that this is the median stack. It's not just 1 or 2 random oddball galaxies that are emitting helium-2. This is more than a dozen galaxies, and we are seeing these really hard lines in the median stack. The low escape sources had no signs of these very hard lines. And what this is telling us is the high escape stack must really be powered by the most massive stars, very young, order of 10 megayear populations, produced in very fresh starbursts, providing an empirical link to all the talks we heard about burstiness being linked to Lyman continuum escape and all the work from simulations that has been suggesting that picture. The other reason these really hard photons are a total game changer is because they escape really easily. So what I'm showing you on the left here is an SED that is matched to our stack's properties. So you see a lot of helium-2 flux. And what I'd like to draw your attention to is the Lyman continuum transmission. So at the Lyman edge, you might be measuring an escape fraction of about 40%. But for these very hard photons, the escape fractions are like 90%, because the photoionization cross-section is just so low for these very hard photons. So accounting for this effect, totally boosts the escape fractions we are measuring close to the Lyman edge based on all these indirect indicators, like, for example, from the green pea sample. So the key takeaway from this whole exercise, I would say, is we bound the Lyman edge escape fraction for our high escape stack to be between 20-ish% and 50%. So the lower limit comes from selection. So we selected them to have more than 20%. And the upper bound comes from that argument about the Lyman alpha escape fraction being a pretty stringent upper bound. And then we convert this Lyman edge escape to a total escape across the entire ionizing continuum. And that gives us these figures. So for basically half the greater than 0.2 L star LAEs at redshift 2, you get these numbers, escape fractions between 40 and 75%, and a psi ion that is among the highest recorded for any population at any redshift. Remember, the psi ion is adjusted for this escape fraction. This is eminently extrapolatable because Lyman alpha luminosity functions are remarkably stable between redshift 2.5 to 6. So the relative fractions of faint and bright sources in our stack are very comparable to those at higher redshifts. So that is one prong of the argument. The other prong of the argument is that Lyman alpha profiles that are intimately linked to Lyman continuum escape are also redshift invariant, it seems. So there's a beautiful paper from Matt Hayes recently who demonstrated that the entire evolution of Lyman alpha line profiles can be explained purely in terms of the IgM transmission. So putting these two things together, we can extrapolate and get out an emissivity from redshift 2 to 8. So you see this beautiful flat emissivity that is really difficult for reionization models to match, but it just falls out naturally from the flatness of Lyman alpha luminosity functions. And the way to think about this is the steeply falling star formation density is counterbalanced by the rising Lyman alpha fraction in the overall star forming population. And you get out this very coherent picture of how the ionizing emissivity should evolve. So in my last minute, I just want to preview two JWST programs that are also going to be placing some really interesting constraints on the ionizing properties of these EOR galaxies. So this program that I'm leading along with Yarit is focused on COLA1, which is a bubble with a very strongly constrained size. So we've heard about a lot of ionized bubbles in the epoch of reionization, but this is the bubble that we have a really good sense of the size for. So it's a situation that's like a Stromgren sphere. We have a sense of the size, so we can back out what the total ionizing budget is, and we can see whether it's coming from galaxies like COLA1 that are very bright or from many other fainter galaxies. I also want to emphasize that this is going to be one of the deepest NIRCam grism pointings in cycle 1, so it's going to be a great pathfinder for what future deep grism surveys can produce with JWST. The other bubble is the redshift 9 LAE that we heard about yesterday in Rebecca's talk. So it's an LAE at redshift 9. So the question is, why do we see Lyman alpha when the universe is so neutral? Our hypothesis is this is one of the first ionized overdensities where cosmic dawn broke first. And to test this, we're going to run a blind F44W grism survey to get O3 redshifts and H beta psi ions. I also want to highlight that this is going to overlap with Sears in about 50% of the footprint. So that's going to produce really amazing science because it's going to be like the Spitzer IRAC bands, but with grism. So that's going to be fun. And I'll leave my conclusions here. Thank you so much.
All right, so we probably just have time for one question. So there's a question about whether you have IFU data to study the environment of these objects, and would you expect to see a difference between the galaxies with low or high escape fractions in IFU data?
We don't have IFU data currently, but that is something we totally like to look into because the Lyman alpha emitters in general are more compact compared to the general galaxy population. So their sigma, their star formation surface density, is indeed higher. But even within Lyman alpha emitters, is there a difference in compactness? That would be really interesting to look at. And also to look at how diffuse maybe the Lyman alpha halos are. Maybe in the leakers, they're much more compact compared to the non-leakers. That is what my expectation would be.
All right, well, there's plenty more questions in the Slack for you to check out later.
Yeah, thanks a lot, Rohan.